Hi audience and student. This is lecture 13 entitled with design optimization of the current mode control. So we take one example using buck converter, and somehow I prefer classical design approach and the classical model. So that is easier to understand and that is easier to simulate using some cheap software like PC. Okay. So for the classical design, I select this. Okay, ratio between current loop crossover frequency omega Ci to switch frequency omega S is 0.5. Okay, if you want to translate this thing into new design, that is the same as QP of 1. This is a very popular number in industry. So without knowing some every details about the sampling effect, they use this number. Okay. I use term design optimization. Okay. So we'll discuss loop gain shaping and output impedance analysis with different omega CR selection. Omega CR is crossover frequency of the loop gain, which is very important parameter. Okay, it determines the dynamics of converter very strongly. Okay, so I'd like to show the performance of converter when this omega CR is varied. So how to select the optimal value of the omega CR? There is no optimal in the world. If you optimize one thing, the other thing will be should pay some price on that. Okay, something like that is design trade-off. So I'd like to provide you information about the design trade-off, okay, by the selection of loop gain crossover frequency. And I'd like to show the asymptotic construction of output impedance. And in lecture 14, I'd like to discuss the relationship between output impedance and the step load response. I think we covered this more than 2 times, but somehow I'd like to repeat here. So the lecture 14, we finalize everything, okay, about this, the current mode control in non-isolated PWM converters, and we'll cover the current mode control with isolated practical converters, flyback converter, optocoupler isolate, offline flyback converter with peak current mode control that will be covered in the next semester. All right, okay. This is the plot of loop gain. This is the expression of the loop gain. The G VCI is control to output transfer function with current loop closed. Because we are using this classical model, there is no double pole at the half switching frequency, but we have this pole, single pole at current loop crossover frequency. Okay, so this is the one case of asymptotic plot of loop gain. Okay, and we are increasing this value of the KB by 2 times. Okay, maybe 2 times. So this one was the original design, and it is increased by 2 times, and it is decreased by half. Then it will change like this. Okay. By changing this KB, if you modify KB, it only, the phase remains the same because this is the constant. It only increase or decrease loop gain crossover frequency. Okay, and this is the omega Ci, okay, which occurs before the crossover frequency. No, this is going, yeah, this is the crossover frequency and after crossover frequency. Okay. So we have 3 different cases, and this is the simulation result. I'm using this previous design, and previous design we used R of 10K. Okay, if you decrease by half, you are increasing the gain twice. All right. If you increase R, if you double this R, then you are decreasing the loop gain crossover frequency by half. Okay, so we have 3 cases, and this is the 10K 5K, 20K, at 10K, this is designed to place the loop gain crossover frequency at omega ESR. This is the design we used, and I think this is the best design. And around that, we increased and decreased the crossover frequency. Okay, so variation of crossover frequency is apparent as you change this one, but this phase is almost the same. Okay, so phase margin remains the same. Okay. Maybe this one is higher, actually higher than this. Okay, but they are about the same. Okay, only this one is changing. Phase margin remains the same. Crossover frequency is increasing. Okay, increasing the crossover frequency while maintaining phase margin sufficiently large is good, generally good, is not always good. Okay, not always. Okay, I'll show the case. Okay, okay. So this is the impact of the loop gain characteristics caused by this. Okay. And this is the output impedance analysis. This is the small signal block diagram of current mode controlled PWM converter. So we know you know this, right? This is for the voltage feedback, and this is for the current feedback. Okay. So we defined the Tm here. We are using the loop gain, only one loop gain T1 here. But actually, this is the two-loop control system. There is one feedback loop and the other feedback loop. Okay. In a single loop feedback system, there is one loop gain, uniquely defined loop gain. But in multi-loop feedback system, many loop gain can be defined. All of them are legitimate to be a loop gain. Okay. Loop and the gain of a loop is different. Okay. Okay. Loop gain has some special meaning. All right. So think about this. T2. Okay. T2. Then you inject the input signal here. Then that input signal is passing through this, and this is coming back to here. That is defined as current loop TB. But there is another path. Disturbance is coming in here. Then it goes through this. There is a loop created here. Then this Tm. Numerator is TB and denominator is 1 plus Ti. Ti is this current loop, not current loop gain. Okay. This is the Mace's gain rule. Okay. So we are using Tm, but we are using different notation T2 because there is another loop gain defined here. Okay. So you inject the signal here, and you are watching this input, this output. Then input will go through this and come back here. There are another one. It goes here and come back here. Okay. There's only one point for the input injection, but there are two passes. So T1 is this one plus this one. T1 is this one plus this one. Okay. So we defined two different loop gains, and you can find another loop gain here. Okay. So in this two loop system, at least there are three loop gains. Okay. But this one is not useful, and this T2 or Tm is useful. And in the past, people think this T1 is very useful. Okay. So one way of analyzing this is consider this separately. Okay. That is very complicated, not complicated, but very cumbersome. Okay. And tedious, and it requires some analysis. Okay. But we are taking different approach. We are including everything, and we consider this is as a new model, and we only use one loop gain defined here. Okay, but in principle, many loop gain can be defined. Okay, so one characteristic of a loop gain is assume this is a loop gain, then 1 plus this loop gain, 1 plus T2 S equals 0 is what? characteristic equation. It defines stability of this system, and this is the same as this one, T2S and the TM is same. And you have this. This is the expression of the characteristic equation, and you multiply this thing here and there, then you have this same equation, then combine this together, so this is the T1S, okay? Then T1S equals 0 is predicting the same information about the stability of the system, okay? So this is the loop gain. This is a loop gain. Ti is not a loop gain. It does not define the stability of the system. So it's not loop gain. Current loop, not loop gain. Okay? So either this one or this one is used, but we are using this, and if we include this everything as the new power stage is the approach we are taking here. Okay? Okay, let me finish up this lecture slide. Then think about the output impedance. Output impedance is a transfer function from here to there with everything closed. Okay, so this is the expression. So this is the input, and this is output, and this is the expression. Okay, so think about the Mason's gain rule. Mason's gain rule denominator is starting with 1, and it has the loop. So there is one loop which is Ti. Okay, it has this minus sign. So you need minus sign in front of this based on the Mason's gain rule. So it becomes positive. Okay, you have another loop here which is TV, voltage loop. So you have negative sign here. So this becomes positive. Okay, there is a denominator. Okay, and in the numerator, feed forward pass is coming in the numerator. So there is one pass here, one pass here. Okay, GP is here, and this is the same as this one, 1 plus loop gain, but this loop should not share the some branch with this one. Okay, because TP, this IO to VO is passing through this, so this loop is not valid as a loop. Okay, so GP 1 plus this loop is okay. This loop is okay. Okay, so you have this one. All right, and there is another pass, forward pass. This one is coming here. Okay, with negative sign here because there is a negative sign. Negative. Okay, so this is the exact expression. You know the older expression of this functional gain block, and you put the expression here, then you are in trouble. Okay, you become dumb, right? Don't do that. Another engineering. Okay. Okay. So try to simplify this. All right. So this is the exact expression of this, and this one. This is Ti. We defined product of this as Ti. So Ti is coming here, and this part is B part is I copied here GQ, and you multiply GID here and divide by GID here. They cancel, same thing. Okay, but this one becomes what? This one is Ti. Okay, so we have Ti is here, and additional term appeared here. Okay, then this expression becomes this one, the same thing. Okay, right? So the denominator remains the same, and this is 1 plus Ti, and this is this one minus GQ Ti times GBD divided by GID is coming here. Okay, and this same thing. Okay, so GP is coming front, and GI is coming here, and it has this term. Okay, all right, this is the same. But you need one approximation. When Ti is much larger than unity, you add 1 here. Okay, it really doesn't matter. This is the 20, then you add 21, and 20 is the same, and you add this because this Ti, magnitude of Ti is assumed to be much larger than unity. So this is valid before the 0 dB crossover frequency of the current loop. Okay? Then this is approximation. All right? This is a genius. This is really genius. Ridley proposed this approximation. Then you can separate this one together, this and this. Okay? Because this is one term, this is another term, and you divide the second term by this one. Then this is the denominator, and this is the this is the numerator. This becomes denominator, and this is what? This is T1. This is T2. Okay? Go separate in two terms by this simple approximation. Okay? This is very smart approach proposed by Ridley with this one. This one, same thing. Okay? And this Ti plus Tb was T1. And Tb divided by 1 plus Ti was T2. Okay? Okay, so you have two terms. When you are comparing with this Ti is T1 is Ti plus Tb, and T2 is Tb divided by 1 plus Ti. So magnitude of this one is much larger. Much larger. Okay, this denominator is much larger, and you compare this numerator GP and GQ has negative sign in front of this. If you derive this, the minus sign is coming here. Okay, so this one is negative. This one is negative. Okay, then this one is much larger than this one. This one is larger than this. Then by this numerator, this one is much larger. Denominator, this one is much larger. Numerator, this one is larger. Then you ignore this. Okay? Then you ignore this. Then you have final expression of this. This is the expression for the output impedance. And this GOIS is coming here. Okay, just 1 minute. And the GOIS is this one. Okay, so you have this. This is the final expression of output impedance. But TMS is this one. Okay, TMS is TB divided by 1 plus TI. Assume TB is 0, voltage loop is broken, and the current loop is valid. Then this one becomes 0. Okay, so this one becomes 0. This one becomes 0. Then this GOI is same as GOS. That means GOI is output impedance evaluate only current loop closed. Voltage loop is open. Okay. We used this in the previous analysis. All right. And we didn't calculate this. I didn't mention this because we need something else. We need the concept of the T1 and the T2 to do this. So I postponed the discussions about this. Okay, so this is our final result. This one. Okay, GOI is output impedance with current loop closed. This can be easily calculated, evaluated. Then with that we finish the analysis of output impedance. Same is true of the audio susceptibility. Okay. Okay. We are in the middle of lecture 13, talking about the design optimization of current mode control. We are dealing with buck converter with classical design, and the target of this design is placing the loop gain crossover frequency at the 50% of the switching frequency, and this target is same as putting QP at 1 in new design approach. So somehow I prefer the classical design approach, so we will follow the classical design approach, but basically they are the same. Okay. So in the earlier part of this lecture, we discussed the loop gain shaping. Okay, and you are talking the beginning of output impedance analysis, and we went through this. And we discussed this. For one reason or another, I modified this lecture slide. I put this lecture slide into two different lecture slides. Okay, so maybe this is slide different from what you have, but you will be okay because this post lecture will be posted in OCW site. Okay, so in this lecture slide, I'd like to discuss the loop gain of the feedback system. Okay. In the undergraduate course, they are only talking about the single loop feedback system. So, for example, this column mode control is not present, then this part is gone. Then this is the single feedback system, voltage mode control. There is only one loop gain here, and the magnitude phase of loop gain is uniquely defined in there because there is only one feedback. Only one loop gain. Okay, and that loop gain carries the information about absolute stability of the converter and the relative stability of the converter. So the implication of phase margin, gain margin, for that case is very clear. The situation is a little bit different. There is more than one loop for two loops. So previously we did this. This was the voltage mode control, and we added this part. It becomes current mode control. This is called two-loop control system because there is one loop and there is another loop here. This is not loop gain. This is just the feedback loop, and this is called current loop. This is called the voltage loop, or this is called the inner loop. This is the outer loop, and this is called the fast loop because the inductor current is fast, and this loop is responding fast, and this is called the slow loop. Okay, so very similar terminology and some confusing terminology. Okay, in this system, previously we considered this part, okay, including this current mode control, this TI. We considered this as a new plan, new power stage model, and we considered this as a single loop system. Okay, so if you put everything inside the black box, and just you are looking at this, and this is the single loop system. Okay, but inside of this there is another loop. Then loop gain. Suppose loop gain is defined here. That is the TM. Okay. In the previous lectures, we just referred this loop gain as just the loop gain. Okay. And measuring this loop gain or simulating this loop gain is done in this way. You cross out this, you break this point, and you inject some sinusoidal signal here, and it goes around here, and goes around here, and come back here. Okay, this is the small signal excitation. This is the measurement of small signal output at that excitation frequency. That is the frequency response, one specific frequency, and you sweep the frequency of this, then you have a continuous curve, loop gain curve. Okay, so this is the one loop gain. Okay, so this loop gain input is here, output is here, and you apply the Mason's gain rule. Then there is a forward feedback path here. That feedback path is coming in the numerator, and denominator becomes 1 plus loop in the system. Okay, so there is only one loop. There is a loop, but this is broken. There is only one loop. So in the denominator, 1 plus Tn is coming here. Okay, this is defined. We defined as Tn, and some people they call it T2, and they call it outer loop gain or slow loop gain. Okay, and there is another loop gain can be defined. You cut this point. Okay, you cut this point and consider everything inside. This is the new model, new power stage model, or something similar to that, and you inject sinusoidal waveform, and it goes around here and come back here, and it goes here and come back here and measure here. This is the input, this is the output. Then there is a one forward pass, two forward passes. One is this, and the other is this. So in the numerator, it Ti plus Tb current loop and voltage loop. Some of them are coming in the numerator. In the denominator, 1 plus loop gain. Okay, loop gain of the loop. But this is broken. There is no loop. Okay, Ti is not existing. This is broken, and the TB is not existing because this is broken. So only this one is loop gain. This is called overall loop gain. This is called outer loop gain. And another loop gain can be defined here. Okay, you break this point and inject some sinusoidal waveform, and this will come back like this. So it comes in the denominator. Okay, this one. No. This is a loop. Okay, so no, this is for the signal path. The excitation is coming in and coming out here, and multiplication of this is Ti. Okay, and denominator 1 plus loop gain of the loop. There is a 1 loop here. Okay, then this is the T3. Okay, so this 2 loop system, there are 3 loop gains can be defined. So which one is best? Which one is a true loop gain? Which one is a false loop gain? That is a very absurd question. There are 3 loop gains, and each loop gain carries the different information about this dynamics of converter. Okay, so there are 3 different loop gains, but they carry the common information that is about the stability of the system. If this loop gain predict converter is stable, then this should be predict the same thing, and this should be predict the same thing, because there is one system, then there is one stability, stable or unstable. Or if there is one system, there is only one characteristic equation, and the root of characteristic equation is called eigenvalue, pole. Okay, natural mode that determines stability of this system. Okay, so this we have T1, 1 plus loop gain equals 0. This is what? Characteristic equation. Okay, and 1 plus T2 equals 0, which is this one. This one is characteristic equation, and 1 plus T3 equals 0. This is a characteristic equation. All of them is the same equation of this form. Okay, so root of this equation should be same. They are the same equation, but stability, absolute stability can be assessed using any of these 3 different loop gains. Okay, but phase margin, gain margin is very different. Okay, so this loop gain, phase margin is different, gain margin is different, crossover frequency is different, shape of magnitude, shape of phase curve are different. Okay, it has different implication, and we can make use of each loop gain for different purposes. Okay, so comparing this and this does not make much sense. They are different things, but the common thing is all of these loop gains predict the same stability information about the system. Okay, so we'll be using this T1 and T2 for the output impedance analysis. Previously, we only used this one, Tm, okay, which is outer loop gain. This is just one specific loop gain among 3 possible loop gain definitions. Okay, in the past, and including me, we rigorously analyzed T1 and T2, their implication, and I know all of this, why they are different, and what they are offering to us, providing what kind of information from each and different loop gain. Okay, but I'll skip that. Okay, that is too long to discuss here, but somehow you understand this. There are many loop gain can be defined in this multi-loop feedback system. Okay, so loop gain has special meaning. The loop gain, 1 plus loop gain equals 0, always carries the information about stability of the system. There is the one common things, and any possible loop gains, they predict the same information about stability of the system. That is also called the unit of characteristic equation. There is one system, there is only one unique characteristic equation. Okay, that root of that characteristic equation determines the stability of this system. Okay, so somehow I direct address this fact. Okay, this is important information when you are dealing with the system which has more than one feedback loop. Okay, otherwise you got confused very much. Output impedance analysis. So in the output impedance, this is the output impedance characteristics. We use the Mason's gain rule. So we covered this in the previous lecture, the previous part of this lecture. And here we have T1, T2 definition or expressions, and we went through this and we find out this output impedance is rearranged in this form. Okay, Ti is current loop, Ti is current loop, and this is the same expression. We split with term having the Ti in front and without term Ti. And one very critical, very important approximation is we replace the Ti with 1 plus Ti, because for the before the loop gain crossover over frequency of the current loop, magnitude of Ti is very larger, very larger than unity. So adding 1 is nothing. Then you separate this part, and we have this. Okay, then this becomes what? This becomes T1. All right, this was T1, and you divide this thing in the numerator and the denominator, and you have this. This is a T2. Okay, so you have this expression. When you compare this, the magnitude of this and this is much larger than this, and this one is larger than this. So you can ignore this whole part. Then with that, we have this. This is the output impedance expression, and this whole thing is denoted as GOIS. Okay. Later on, you will see this is the output impedance of this converter with only current loop closed. There are 4 transfer functions, but this can be easily calculated because they have the same denominator. So denominator will be cancelled easily, and this can be easily simplified. Okay. Anyway, and this is denoted as GOIS. GOIS is this one. Okay. If TMS equals 0, then output impedance is the same as GOIS. That means GOI is actually it is output impedance converter with only current loop closed and feedback. The voltage feedback is broken. Okay. That is the condition of this. With TB equals 0, voltage loop is broken and current loop is active, then this becomes 0, then TMS becomes 0. With 0 TMS, this are the same, then means the GOS becomes same as GOI, means this GOI is output impedance of the converter with current loop only closed and voltage loop broken. Okay, and this one can be easily calculated. So final expression of output impedance is this one. For the older PWM converters, GOS output impedance is GOI divided by 1 plus TMS. This form is very familiar to us. We used this for the audio susceptibility analysis. Output impedance analysis is coming again and again because we are dealing with the feedback system. Okay, so feedback system has denominator 1 plus loop gain. Okay, so this is true for the all PWM converters, and this expression it can be simplified like this. This one, GOIS. Okay, not whole thing. GOIS is this one. It has 0 here. This is ESR 0, and it has pole. Expression of pole is this one, Pi and constant gain. And this table summarize the expression of KOI, this DC gain, and this pole for three different PWM converters, buck converter, boost converter, and buck boost converter. So this is R divided by 2, R divided by 1 plus D, steady state Dewey ratio, and this omega Pi is this one, this one, this one. But usually RC is much, much smaller than R. Then you ignore this, ignore this, ignore this. That is the expression of omega PL. We used this in the analysis of the current loop or the loop gain shaping. Okay, asymptotic construction of the loop gain. We use this parameter. So they are practically the same. Okay, so we replace omega PL with omega PI. Okay, that is very accurate because this one is very small. Okay. So here we have the asymptotic construction of output impedance of buck converter. So this is the buck converter case. We know this output impedance is expressed like this. This is output impedance of a converter. Only current loop closed and the voltage loop is broken. Okay. And for the buck converter, we know this is R. No. Okay. We know this. This is low frequency value. For the buck converter, this is R, load resistance, and omega Pi is coming here, but omega Pi is same, practically same as omega PL. So we have omega PL for, from this loop gain asymptotic plot, and this is a crossover frequency, and omega Ci is loop gain crossover frequency of current loop. Okay, there is an additional pole. This pole is coming in only classical analysis. In new analysis, somehow this pole is missing, and there is a second order term here, but we ignore that. Okay, for this output impedance analysis, coming after this loop gain crossover frequency can be ignored because from this asymptotic analysis, after this loop gain crossover frequency, this output impedance is just following this GOI. Okay, whatever happens here, it won't affect this GO. Okay, it just follows this GOI, which is output impedance of converter only current closed. Okay, before this loop gain crossover frequency, we have subtraction rule. Okay, and you practice this a lot. Okay, so we have the slope difference. So plus 1 slope is here. Okay, and this is the zero slope. Slopes are the same. Then this becomes this horizontal line, and the distance from here, there, this length of this line segment should be same as this length, and this length should be the same as this. Okay, this is what? This is the asymptotic construction of this output impedance, which is this. Okay, if you take a look at the asymptotic plot of output impedance, it has differentiation structure in the beginning, and it has one pole. Okay, this pole is located at omega GC is compensation 0. Okay, it comes from the voltage feedback compensation, and this becomes the dominant pole because this becomes at the earlier frequency than this one, then this one. So we have additional pole here, and we have 0. Okay, so the asymptotic construction of GOS is very simple. We have this line segment of differentiation and the horizontal line segment and minus 1 slope, and this becomes again horizontal line, and we know the value of this. This should be 20 log RC from the circuit model of the converter. Okay, at the high frequencies, this should become to the open loop output impedance, which becomes this at very high frequencies. All right, so this is true. Okay, then this is the expression. Okay, GOS is this one, and this is the equation of this. We used to construct this asymptotic plot of GOI, and this is the final result of asymptotic construction of output impedance. Okay, so we know this equation because this is plus one slope and one pole, another pole, and the zero is coming later. Okay, so everything is very simple and clear. And I did one simulation to justify this construction of asymptotic plot. This is the buck converter you are using all the time. And here, this voltage loop is broken. The current loop is connected through this element. Okay, so internally there is a connection at the output of this to the input of this. Okay, and this is calculated from the maximum value of switch current and the current sensing network gain and the slope of external lamp and the on-time period of the converter. Combining this, you estimate this, you calculate this, and this becomes as the DC component here, and the AC component is coming through this. No. This is the to measure the output impedance. Somehow AC component is coming through this and passing through this, and it generates the plot. Okay, so this is the overplot of three different things, and this is the output impedance with current loop closed that generate this plot, and this is the loop gain plot. I use another program to generate this, and I use another program to generate this. Okay, so this is the overplot of three curves from three different PC models. You know each of these models, how to deal with this for the converter, and you should know this about the boost converter. That is the part of the final exam. Okay, and this plot justifies our previous construction process. Right? So this is the loop gain. This is loop gain crossover frequency, and this loop gain is shaped to have crossover frequency at the omega ESR of the output stage. Okay, so at that case, this omega ESR, so it start to be a horizontal line, and before this, it follows this, and before this, there is a subtraction rule. Okay, so distance, this guy is same as distance. Length of this one is the same of length of this one, and this frequency is omega PL is here somehow. It's not shown here. Okay, but omega PL is here, and this is omega GC. No, this. Let me do this. This is no. This is not omega PC. Oh no, this is true. No. This is omega GC. Omega PL is not appear here. Okay, so this omega PL is not okay. Is it there? And omega GC is compensation zero is occurring here, right? And this is a loop gain crossover frequency, which occurs at the omega ESR. Okay, so this is justification of this. I would intended to say this omega GC becomes the dominant pole at here. Okay, but this is the special case, and for three, I simulate or analyze three different cases. This is the case we covered in the previous lecture slide, where this loop gain crossover frequency occurs at the omega ESR. In that case, the output impedance was something like this. Okay, so this is clear from the asymptotic construction of this output impedance. Okay, and this is a case where this omega CR loop gain crossover frequency occurs before the omega ESR. This is the asymptotic construction of output impedance, and this is the final case. In this case, this omega CR occurs after this omega ESR. So we have three different cases of output impedance asymptote. Okay? This is not difficult. Okay? Follow this procedure with different cases. So this mid one, we covered this in the previous lecture slide. And for this case, the omega CR is below this one, then you have this structure. If this omega CR is before this CR, or this omega CR comes after this omega ESR, you have this structure. Okay? 3 different cases will occur. Okay? But very important factor is this first pole always occurs this omega GC. Okay? For 3 cases, this becomes the dominant pole. So dominant pole always occurs at the compensation 0 of voltage feedback compensation. This will determine the speed of step load response. Okay? Because this is the dominant pole, determines the transient response of this system, step load response system. Okay? How about the peak value? Okay? For the case number 2, where this omega CR occurs at the omega ESR, the peak value is the same as high frequency asymptote of output impedance, which is this one, but this is the same, very similar to 20 log RC. Okay, because R is much larger than RC, you are seeing just a smaller guy. Okay, so for this case, the maximum value of output impedance is this one, and maximum value starts from here, and it stays at the maximum value here. Okay. For the case number 2, where this loop gain crossover frequency occurs, after this omega ESR, you have this kind of structure, but this maximum value of output impedance remains the same as this case, which is this one. For cases 2 and 3, the maximum peak value of output impedance is determined at high frequency, and that is actually the high frequency asymptote, which is practically same as RC. Okay. How about case 1? Case 1 is this one. Case 1 is this one. Case 1 is this curve. Okay. So in this case, the maximum value is larger than this one. Okay. The maximum value is larger than this high frequency asymptote, but there is a relationship. Suppose this is the maximum value. So this is the maximum value. This is the horizontal line. So maximum value is declining from this frequency to this frequency by slope of this. That becomes this one. So you have this simple equation. Okay, this is not just the graphical interpretation of this distance. Then this becomes this linear equation. Then this becomes this. Then maximum value of this the output impedance of case 1 is simply this one. Okay, so we know all the maximum value and the corner frequencies, because the maximum value of output impedance and dominant pole of output impedance, there are 2 important parameters to evaluate the transient response due to the step change in the load current. Okay, so we have 3 different cases. This is the case 1, this is case 2, case 3. Okay. Simulation result. This is a setup to simulate the output impedance with R as 20 is it has the low integrated gain, middle integrated gain. This was our previous design. This is the highest integrated gain. So integrated gain is increasing, phase remains the same because we are only changing this one. So this becomes 2 times increased, 2 times increased. R is decreased, but integrated gain is increasing. All right, 2 times increase, 2 times increase, and this is GOI. Okay, this is the TM. Let me write down this here. This is a TM. This is the GOI. This is a GO. Okay, so the shape here shown here is exactly same as this one, okay? Because some distance between this pole and this pole, it has we have some rounded top, okay? But in asymptotic float, they are the same, okay? This is a case 1, 2, 3, okay? 3 different cases. And I repeated this part, okay? So with different R's, this is the output impedance for the case of R of 20K, 10K, 5K, this becomes larger. It has larger integrated gain, and the shape of this output impedance is changing, okay? Which one is best will be explained in the next slide and in the next lecture. This is the part. This is actually the introduction of next lecture. So we have 3 different cases for the output impedance. Okay, this was case 1, case 2, case 3. And the analysis this is very easy because we have this asymptotic. We construct the asymptotic structure of this, asymptotic structure of this, asymptotic structure of this. That means we know the transfer function of this, or we have very close predictions for the transfer functions of 3 different cases of output impedance. If we have the expressions for the output impedance, we use this formula. Okay, this is the transfer function from the load current to output, which is called output impedance, and this is the S-domain expression of step change in the load current. Multiplication of that is S-domain expression of our voltage. If you take the inverse Laplace transformation of that, you will have our voltage waveforms. Okay. This is a simulation. Okay, but you can calculate this. All right. Let's take a look at the simulation result. Okay. So this is the case A, which has the largest peak value, and this is the case 2, which has this, the omega ESR and omega CR occurs at the same frequency. This is case 2, okay. This is case 3, this one, okay. If you take a look at the peak value of this peak value is largest in here, okay. So in terms of peak value, this is the worst. And peak value, this one and this one, they are the same. Because the peak value of this output impedance was the same for the case 2 and case 3. Because of that, the step response, maximum deviation output voltage length of this is the same here, okay. And this shows the pattern of load current step changes, okay. So it increase, decrease, and the size is I step here, okay. So, and in terms of the response time, you may think this is the fast, okay. This is the most fast one, okay, and this one is the second, this one slow. But if you compare the settling time, initially this is slow, initially this is the fast, but finally reaching the some finite percent of the steady state value, if you consider this is the time, settling time, then settling time almost remain the same. And settling time is determined by the compensation 0 of voltage feedback compensation circuit. Okay, this is the same, right? And you can see there is a jump here. So this sudden jump here, okay? There is a sudden jump, okay? You know how to predict this. I think I explained at least once, more than once, okay? This is called initial jump, and the size of initial jump is final value of output impedance times size of the step change, okay? So this is change. Initial jump is the same. Initial jump is the same. Initial jump is the same here. There is an initial jump, and it is increasing in exponential function like this. But this you take a look at initial jump here. They are all the same, and initial jump always occurs in this fashion. Okay, this is true, always true. Okay, but for this case, this value becomes the peak deviation. This value becomes peak deviation, but peak deviation here is larger than this value. Okay, that the difference is coming from the difference in the peak value of this output impedance. Output impedance peak. This one the same. Then this the initial jump is the same, and the initial jump becomes the peak deviation in our voltage. But this one, initial jump is the same, but the peak deviation is larger than the other two cases. Okay. All right. So this is the summary of this lecture. Somehow we focused on the analysis of output impedance and the relationship between this output impedance and the step load response will be discussed in full detail in the upcoming lecture. Okay, so you know how to select the loop gain crossover frequency. Okay, in consideration of output impedance and step load response, the similar analysis can be done for the audio susceptibility, but the result becomes very similar to this. Okay. Probably this will be the best selection for this case. Okay. All right.